The launch of the James Webb Space Telescope, which has been long anticipated, has ushered in a new era of exploration into our cosmos and aims to debunk old theories concerning the dark matter. For example, before we had fancy-pants instruments like Hubble and James Webb, we thought it took 300 million years to form stars, but that's been proven wrong on countless occasions. But how could scientists have been so wrong? Today we'll be talking about how James Webb has debunked past hypotheses on dark matter and what we could discover moving forward. Carnegie Mellon University Associate Professor of Physics Matthew Walker, the principal investigator of a program using data collected during the Hubble Space Telescope's first year of operation, is one of the many researchers planning to use the data from the Hubble Space Telescope's successor. The top-level scientific ambition is to determine what dark matter is like with the James Webb Telescope. This hypothetical kind of matter has never been directly discovered, although it's thought to make up most of the universe's stuff. According to several hypotheses, the presently emerging dark matter hypothesis predicts that dark matter exists in clumps called halos, in small basic units rather than humongous galaxy-sized agglomerations. The presence of these so-called subgalactic dark matter halos, which people have been attempting to test for decades, is one of the fundamental predictions scientists are hoping to test with the dark matter with the help of the James Webb Telescope. These lower-mass dark matter groups lack stars, making them extremely difficult to detect and monitor. Yes, even with the James Webb Telescope. Scientists have noted that 2 experiments have been conducted to look for subgalactic dark matter halos, but both have produced vague data. Scientists constantly search for disturbances from these subgalactic dark matter halos on extremely delicate gravitational systems using the James Webb Telescope. In other words, these are wide binary stars, consisting of pairs of stars circling each other but separated by more than 1,000 times the distance between the Sun and Earth, making gravitational interactions between them exceedingly weak. Why are these wide binary star systems being researched? Scientists are particularly interested in this because these so-called wide binary star systems suggest that if a subgalactic dark matter halo passes across the area, its gravitational forces might be more than enough to annihilate the entirety of this wide binary system. Matthew Walker is one of many researchers planning to use the data from the Hubble Space Telescope's successor to study these binary systems for a better understanding of dark matter. How are they doing this? Walker and his colleagues are examining data from the James Webb Space Telescope to see whether any broad binary star systems can be found in dwarf galaxies, which are thought to be dense in dark matter. If they are discovered, the cold dark matter hypothesis will become increasingly implausible. Trumping some old theories thanks to these new studies with James Webb, dark matter might be made up of ancient black holes, a hypothesis that has been recently brought back into the spotlight. The observations from NASA's James Webb Space Telescope might reveal that numerous black holes were created during the creation of the universe when the Big Bang occurred. These findings might explain dark matter's gravitational effects. Many particle physics models use what are known as weakly interactive massive particles, which are heavy, slow-moving theoretical particles that pull on the conventional matter using gravity, just like how our planet pulls us towards its core to keep us grounded. But according to Benjamin Leman, a physicist and PhD candidate at the University of Santa Cruz who researches dark matter and particle physics, that interpretation has been in growing tension with recent experimental results. As a result, the particle physics community has been keen to investigate other dark matter possibilities, including revisiting old theories using new research models. Did you know that Stephen Hawking theorized in the 1970s that concentrated regions in the super-hot, compact early cosmos might have formed the first black holes? The formation of primordial black holes at the beginning of time is based on the basic fact that the large-scale structure of the cosmos is the product of minuscule changes that occurred shortly after the Big Bang. According to this hypothesis, pockets of these fluctuations would reach a critical density, ready to collapse into black holes. Still, the extreme heat around them would prevent them from collapsing instantly. Particles become so hot that they are zipping around like crazy, unable to collapse into black holes until the universe spreads out and cools enough to allow them to exist. At least that's what Günter Hasinger says at the European Space Agency's Director of Science and lead author of the new study is to be published in the Astrophysical Journal. According to Hasinger, the collapse would occur only when fundamental particles known as quarks can merge into protons, which would have commenced when the cosmos was only a fraction of a second old. According to Nico Capilouti, an astronomer at the University of Miami who led the study, the team set out to discover if the universe we observe today could have been created with this new cosmology of primordial black holes. Their simulation revealed that a world with primordial black holes serving as dark matter might resemble ours. But dark matter and primordial black holes are not mutually exclusive. One type of dark matter that might exist, though, is primordial black holes, and that's why it's important to have an understanding of them. The sheer number of scientific questions that might be investigated with this one model is incredible, and the study's methodologies are also rigorous among astrophysicists. The Hassinger team's model predicts that stars take about 50 million years to develop, which is significantly faster than traditional models' prediction of 300 million years. According to Cappelletti, another scientist on Hassinger's team, scientists may be able to clarify this discrepancy by taking a closer look at the universe's remote and ancient reaches. The James Webb Telescope, which will look at signals from more than 13.5 billion years ago, might provide a link between Hawking's decades-old theory and dark matter. Researchers didn't have a genuine sense of scale when Hawking initially hypothesized primordial black holes. They assumed the black holes formed would be extremely small, so scientists researched for gamma rays produced by tiny black holes in the years that followed Hawking's research. Most scientists put the notion on hold for decades when they couldn't discover them until Hubble and JWST arrived. Scientists later learned that primordial black holes can be of various shapes and sizes, including much bigger ones. According to Hassinger, the theory of primordial black holes acquired a lot of support following the initial gravitational wave detections, which revealed that black holes are heavier than scientists predicted before. Again, all thanks to the advanced scientific instruments on the JWST. But a physicist who goes by the name of Cappelletti claims that even with today's cutting-edge telescopes, scientists still have a large gap in their understanding of the early cosmos. Astronomers can only see the last 13 billion years of the universe's existence, even with the JWST, although it's estimated to be around 14 billion years old. He claims that the missing billion years are riddled with unsolved mysteries, such as how we came to have black holes billions of times the sun's mass. Moreover, the origin of these supermassive black holes is exceedingly difficult to explain using existing physics knowledge. Still, the JWST may help us get a bleak understanding of them, at the very least. Hassinger is optimistic that the James Webb Telescope will detect more and more stars in the deep field, a dark area of space where the Hubble Space Telescope discovered many of the oldest recorded galaxies. If that happens, it will almost certainly happen this year. The JWST has found a cluster of stars, and it's only in its first phases of aligning its instruments since its launch. How amazing is that? According to Cappelletti, James Webb will peek into the windows of an ancient age of time. If it is discovered that protogalaxies are far more numerous than expected, their quantity and characteristics may be a good sign of whether primordial black holes exist. However, according to Cappelletti, the smoking gun will most likely be the finding of gravitational waves from a primordial black hole in the future. According to Lehman, James Webb may test the popular hypothesis on black holes, which has exciting potential. But of course, this won't completely answer whether dark matter is made of primordial black holes. But scientists don't typically aim to prove their hypothesis right. Instead, they come up with another hypothesis to try and gun it down. The fact is that the more times an attempt to debunk a hypothesis fails, the more solid it gets. The idea persists if it can't be refuted until the next generation of experiments and discoveries emerges. Whether or not the JWST team's idea is proven right, the next discoveries might represent a watershed moment in the hunt for primordial black holes and dark matter. We'd be in trouble if scientists studied the deepest Webb findings and didn't discover a hint of a departure from the conventional model of black holes research. While we could go on and on about all these exciting discoveries that will emerge in the years to come, this is gonna be it for today's video. Thanks for sticking around until the end. Please leave a like, share, and subscribe to our channel for more awesome content just like this. Please let us know in the comment section below what you think the JWST may discover next, and if you're excited to learn more about our universe.